Okay, everybody. I am recording this from my computer, so I'm going to try to, if somebody asks a question, I'm going to try to remember to repeat it because I've only got my microphone here. So, yeah. You don't have access, meaning you can't download it? I just gave everybody can edit. Oh, you're not in the email list. Well, that's the issue. I only sent it to people that sent me an email. How many people sent me an email telling me they wanted to be part of this? I think, did you? If you have not, please, I will give you access to the folder right now, but I need your address, your email address, or you sent a request? You can if you want, yeah. I don't want to share. Okay. So if you sent me an email letting me know that you are interested in taking part, then you should have received a message saying you have access to the educational version of the ThermoCalc install files. If you did not, please come up here and I will send you that right now. Unless you are sending, unless you have that, and I don't see, I have not seen that request yet. So, okay. Can you send me access to my email? Yes, let me get this up. Once I figure this out, okay, so grant access. Please just type in your email, and then you can type in your email, and then everybody will have access to it. Oh, sorry, what's that?
Thanks. Sorry.
Yeah, no problem. I figured this was going to be what happened at least the first time. So for everybody that's watching this at home, haha, you're going to watch us install ThermoCalc for the next 20 minutes. Perfect. All right. Go ahead and add yours. So if those of you that have access, can you download it and install? You still can't? Yeah. Oh, okay. That'll work. Was anybody else not able to download it from that link? I know some of you have the full version. Once we get these emails sent out, I will. All right. All right, so the four of you should just have received access, and so I'm assuming that most of you are currently downloading and installing, and it's relatively slow. Ah, here it is. Okay, I just received one. All right, so. All right, so while everybody is downloading and my computer seems to be slow opening it up, why don't we go around the room starting with Nathan over here and introduce yourself, what your major is, a lot of material science, but maybe not all, and then who you're working for. What's your major? Ooh. I'm technically your co-advisor. I'm technically your co-advisor. Oh, excellent.
I am Ryan, also in Dr. Nathan's group, also a nuclear engineer.
I have received a lot of people from Dr. Zinkel's group, which is very, I think he sends everybody. If he doesn't send everybody, he's got, which he may not, because I know he's got a huge group. Okay, so most of you know me. If you don't, you heard from your advisor, but I'm Dr. Lass. I'm an assistant professor of material science and engineering, specializing in phase transformations and microstructural evolution, using both experimental and computational thermodynamics and kinetics. So I'm a blend of both. I don't like to call myself an expert in ThermoCalc, but I'm an avid ThermoCalc user. And so I've found it very, very useful over the course of my 20-year career now. And so I need to pass this on because it's a very useful technique. And I would be willing to bet that at least half of you will find some use with it if you haven't already. So does everybody have access to a version of ThermoCalc? Okay, so I have provided access to the educational version to everybody. You can also go to the ThermoCalc website and download that educational version yourself. Some of you do have access to the full ThermoCalc version, and that's because you've been working with me already. For those of you that like the software and want to start using it for your research, that's great. You just need to come let me know. I will give you access to the full software, and you can download that software and you can use the full version. The only request is that I become a collaborator with you on all publications that you published with that. So I'm a co-author, which is good for me, but it's also good for you because not only do you get access to ThermoCalc, but I spend a good amount of time talking to students about their specific applications. So giving them a little bit more one-on-one help. So that's what you get for using ThermoCalc and putting me on your down as a collaborator. So any questions out there before we get started? In the folder that I sent to you, I gave you access to the educational version of the software, or the educational folder, right? So if you're a Mac user, and so there are 3 different installation files in here. There's ThermoCalc-educational-Linux for somebody that's using Linux. There's a zip folder containing the files required for a Mac, ThermoCalc-educational-OSX, which I see that you have a Mac, so that's what you want to download and install. And the third file is ThermoCalc-educational-Windows-64. And for Windows user, that's the one that you download and install. So I've realized that how many people are still getting things installed? Okay, so no problem. So what I will do to start with is I will just give you an overview of what the software is. ThermoCalc is based on the CalFAD methodology, which stands for calculation of phase diagrams. And this CalFAD methodology started back in the 1970s, and it uses semi-empirical descriptions of the free energy of different phases within a system. So most of us have some understanding of material science. So if we think about iron and nickel, one is BCC, one is FCC. So the CalFAD methodology will build a thermodynamic description of the free energy of BCC iron, which is basically they take the experimental data available for pure iron for heat capacity, and they will fit that data to a curve, to a function, and that function is based in physics. So there are terms in there that are based in physics. Now, for the last 40 years or so, computing power has been difficult, and so they did not use something like the Einstein or the Debye model to actually fit the function all the way down to room temperature. So everything we do here will be valid for temperatures above about 250 K. Below that, they use a T times ln of T term to manipulate the low temperature behavior, and so things go wacky. So if you plot, like one thing I can do a single axis, and I'll just show you what happens. But anyway, the way the CalFAD method works while I wait for this to load is we start out with the pure elements. So in 1991, Alan Dinsdale published a paper that had the what we call the lattice stabilities, which is basically the Gibbs free energy of all of the different elements in all of the different crystal structures. So if you go look at this 1991 paper, you go look up silver. Silver is FCC in standard conditions, room temperature, atmospheric pressure. The first free energy that will give you is the free energy of the FCC phase. And you have this function of the free energy as a function of temperature. It'll then give you the free energy of the liquid phase, which has been modeled after measurements of heat capacity and so forth for liquid silver. And then it gets a little bit trickier. They use either extrapolation, or a long time ago they were using some empirical relationships to try to come up with a description for the Gibbs free energy of unstable phases, like BCC silver. Now, in some binary alloy systems, you have a BCC phase. So you have silver in a BCC phase. And if you know anything about thermodynamics, you can extrapolate back to pure silver and get an estimate of what that BCC silver free energy should be. So they've used a combination of that, maybe some DFT calculations. Now, back in the 1970s, they didn't have that, and some other empirical relationships to come up with free energy descriptions for the phases that you don't see in nature. So for everything that we're going to talk about, there's a free energy description for the pure elements. And it's based primarily on the heat capacity of the material that we've seen. Do you have access to ThermoCalc? Okay, perfect. So from those systems, we then put together binary alloys. And if you've taken a chemical thermodynamics class, you've heard of a regular solution, maybe. So if you take my phase transformations class, you learn that the free energy of a binary system is very, very similar to the regular solution, except for your regular solution constant is no longer constant. That constant can now be a function of both composition and temperature. And it's actually a polynomial function. It looks a lot like the enthalpy of or the regular solution constant. And actually, one of my first papers, I was actually connecting these CalFat interaction parameters to atomic level interaction parameters. So if you think of AA bonds, BB bonds, and AB bonds that I was talking about this morning or on Monday in my phase transformations class, you can relate those bond energies to these interaction parameters. And then from that, you build up binary alloys, and then from there, you put ternary alloys together. And every time you do this, people have done this over the last 40 years. They take all the experimental data available for a given binary system. And that could be, enthalpies of mixing. It could be equilibrium compositions of phases in a two-phase field. Anything you can think of. And use that as input data. And all of the interaction parameters are variables, and then they optimize that and come up with a set of free energy functions for all of the phases in that binary system. It's a very, very, very difficult process. I've tried to do it for a simple binary system before, and I think I failed. It never got published. So it's hard. I don't recommend anybody going into it. But if you like that sort of thing, it's tedious, but it's very useful for people like me. You take those binary systems, you put them together, and take any ternary experimental data, and there's an additional set of interaction parameters that are used to improve to describe a ternary system. And obviously that gets a lot harder because now you've got two composition variables, you got even more phases, ternary intermetallic phases that you may have to think about. So it gets really, really complicated. And for the most part, CalFat thermodynamics stops at ternary systems. So we have our unary systems that have pretty much been the same for the last 30 years. We have binary alloy systems, most of which are fairly well described. Maybe not all of them, especially if you're looking into some crazy rare earth systems, perhaps aluminum cerium or something like that. The binary alloy systems are not very well described. And then for most of the primary alloy systems, iron-based alloys, nickel alloys, aluminum alloys, titanium alloys. The most important ternary systems are all well described. And you'll find that if you go in and look at the databases, the systems that you would expect to have been studied over the last 100 years because they're technologically important, those are the ones where we have ternary thermodynamic information. Those are the ones that have ternary thermodynamic assessments. If you're going into a ternary system that's never been looked at, or if you're going into high entropy alloys, like refractory high entropy alloys, there's some weird things going on. A lot of these systems haven't been assessed. So you have to take the results that you get with a grain of salt, because no matter what you do, if you take your high entropy alloys database and you plug in, say, niobium, tantalum, manganese for some reason, it may not have a ternary description for niobium, tantalum, manganese, and I'm pretty sure it probably doesn't because nobody looks at manganese in the refractory alloys. But it will have a description for niobium and manganese. It will have a description for molybdenum and manganese, and it'll have a description for niobium and manganese. And so it will use those binary systems to give you what it thinks should be the ternary phase diagram. And a lot of times that's not bad, okay? Ternary systems, you tend to see a lot more discrepancy. But when you get to higher order systems, if you have well-described ternary systems, the last 100 years of thermodynamics and phase transformations research has showed that you really don't need much more beyond a ternary system. There are some quaternary intermetallic compounds, but they're very few and far between. The problem comes when you're trying to add a new element to a intermetallic phase. Maybe it's a ternary intermetallic phase, and you're trying to add a quaternary element, and that intermetallic phase doesn't exist anywhere where this fourth element is. So aluminum, cerium, copper, got several ternary intermetallics. We also put zinc in aluminum cerium alloys, or nickel in aluminum cerium alloys. So if you wanted to try to describe the thermodynamics of one of these aluminum cerium copper phases that's unique to the aluminum cerium copper phase diagram, and you wanted to describe how does nickel or zinc behave in that phase, you can't do it because that intermetallic phase is only found in that specific ternary system. And that's where nowadays we have DFT calculations. So for systems of interest, alloy elements of interest, people will do DFT calculations. They will calculate enthalpies of formation for these hypothetical intermetallics. And we can use that information now as input to improve our thermodynamic descriptions. So that's just a brief introduction to the thermodynamics. I'm not going to go into detail. If you're interested in that, I actually have a course, a full course on ThermoCalc that I have it online, and I think we go through some of that. But for here, I'm teaching you the basics of how to use it. And one of the most important things that you need to understand is I can't teach you to be an expert. I can teach you which buttons to push. I can give you a general understanding of the types of things that we can do. And then it's up to you to go dabble. When I started with a 2-hour demonstration by a postdoc in my group. And we learned how to calculate a binary phase diagram and some free energy curves as a function of composition. And after that, it was a little bit of help here and there. If I needed help, I'd go talk to a more senior person in the research group. But other than that, it was dabbling, right? So I will give you the tools to do these types of things, and then it's up to you to spend the time to get as deep into it as you really want. Any questions on that? Okay. So I'm going to start by just giving you guys a tour of what the graphical version looks like. Excuse me, what the graphical version looks like. Does everybody have it installed now? Did I talk long enough? Uh-oh. Oh, no. Has anybody else got a Mac? It's a Mac thing. You just downloaded and installed it? You didn't get an error? Did you download it from the website, didn't you? Did you have to input your information for the educational version? If you go to thermocalc.com, you can the other Mac user here, you're Sydney, right? Cool. I will eventually remember everybody's name, but it won't be today, I promise that. But if you go to thermocalc.com and search for the educational version, you can download the Mac version yourself, and that seemed to work for Sydney. So try not using the version I did. I was hoping that would be easy and not everybody had to give their email to ThermoCalc, so you get tons of ThermoCalc emails. But apparently it's more difficult for Macs. And I will say it is not necessarily Mac friendly. When you get to the full version, I have one of Zinkel's students right now, Ty, who is seriously struggling to get the full software to work. And actually, I just got an email today. We're going to give him a single use machine only license so that he can do his work, because he's way off campus anyway and never comes in. I do have a dedicated ThermoCalc computer in my lab so that somebody that doesn't have the full version on their own computer can access it. We'll talk about that when we get to the point where people are wanting to install the full version on their own computer. All right, so there are two different modes of ThermoCalc. There is this graphical mode that has improved significantly over the last several years. It used to be just a shell of the software and had a few features. You could calculate a phase diagram and maybe plot the free energy curves, but that was about it. It's gotten a lot better. I still use the console mode. Which is basically a programming interface with its own little language. This is what I grew up on. I may go into this and start using console mode so that you know some of the commands, because everything that you can do in the graphical mode is basically calling functions from the console mode. And one of the beautiful things that I've been unable to utilize myself with ThermoCalc is that there is an interface with Python. So you can call ThermoCalc using Python, run a batch of calculations, collect a data set, and then you can look through that data set, find things of interest. I've not been able to do that because I'm a dinosaur, and the only programming language I ever learned was Fortran 90, and I haven't used it in 22 years. So we'll start with the graphical mode today. And so the graphical mode, there are a lot of different types of calculations. Getting started, there's an online help. There's example files I'm going to go up here to help and open the manuals folder. So in this manuals folder, all ThermoCalc documentation, you have a PDF file of the examples. I don't know much about the graphical mode examples, but I know a lot about the console mode. And so there are lots of example files included with ThermoCalc that you can do specific things. You can calculate a binary phase diagram. You can calculate the free energy of phases as a function of composition or temperature. You can calculate a ternary phase diagram. And if you want to do something, if you want to use ThermoCalc to do something, chances are very likely there is an example that can teach you how. This is how I have learned how to do lots of different things. Let me close this up. So text 1, calculate the binary iron carbon phase diagram. That's one of the things that we'll do. Plotting thermodynamic functions, that's one of the things that we'll do today. Maybe today we'll get to plotting a ternary phase diagram, finding the miscibility gap, all these different things. And you get down here to more complicated things. For some reason my computer's being slow. I think it's because I have a slow charger. I may have to switch chargers and have a fast charger for this. By the way, this is not what I wanted. I wanted to be able to sit around the table with all of you, but this computer isn't working. So I have to be up here with my computer. So I apologize for making this sound like a lecture, because I don't want it to be a lecture. I know at least the first week it might be, because we're all kind of learning. But if you have any questions, please feel free to stop and ask, okay? So we have different types of calculations. We have equilibrium calculations. So a single point calculation would be, we click on that. Over here, we have a tree of our project. And when you click on one of these different modules, it will create a branch on your tree. The first branch on the tree is always going to be system definer. And under system definer, it's exactly that. If you have it up and running, you can follow what I'm doing. Under databases here, I have a ton of different databases to look at. Let's go down here and we will, I don't want to do the iron carbon because everybody does that. So we'll take the aluminum alloy database, and everybody should have access to the aluminum demo database. Down here on the periodic table, you will see that some of these elements are grayed out. That means the element's not in the database. The elements that you can select are available. So I'm going to select aluminum and copper. And if you want, over here on the right-hand side of the periodic table, you can actually define a material if you're using a specific material. Let's use aluminum 4 weight percent or 4 weight percent copper. You can define it in whatever you're comfortable with. Default is mass percent. If you wanted, you could do it in mole percent, mass fraction, mole fraction, whatever you want. Under species, I've never used species. Usually if I select aluminum and copper, it's the only species I'm going to be dealing with. Other than there is a species called a vacancy. And that is there for both interstitial reasons. So iron carbon system is an interstitial solid solution. So carbon fits in the interstitial sites. So the FCC phase actually has two what we call sublattices. It has your typical FCC sites on your sublattice, of which there are 4. And then it has a separate sublattice for the octahedral. I think it's the octahedral. It might consider both octahedral and tetrahedral together. I can't remember for sure. But it has a separate sublattice for the interstitials. And if you don't have a interstitial element defined, all those interstitials will be filled with vacancies. There are also interstitials on the substitutional sublattices, because in some order-disorder systems, like the B2 phase that you see in nickel aluminum, the vacancy plays a major role in the composition range over which B2 is stable. And so there's a vacancy associated with those substitutional sites. And so we have a vacancy defined. I never play with the species. If you start working on oxides or ionic solutions, you may start seeing different species because they will define like Fe+2, Fe+3 as different species. And if you're doing that, you'll have to come talk to me, and we're going to have to spend some time on it because I've never done that. But it is doable. There are oxide databases. I don't know if we have any of the oxide databases as an oxide demo, but we can think about getting one. They're relatively expensive. So under phases and constitution, it lists all of the potential phases to have, and there are lots of them. The ones that are grayed out are listed in the binary system, but are not useful because they don't have one of the other elements that's required. Like I just saw an aluminum copper. Here's aluminum scandium silicon phase. So that's defined in here. Copper is probably a substitutional element on one of those sites, but we don't have scandium or silicon, so we don't have to worry. And so it just grays that out. See, we have a lot of phases. This Al2Cu C16 phase, that's the theta phase. So if you know what the aluminum copper phase diagram looks like, you'll see it in a few minutes. That's the theta phase. These are all different aluminum copper phases. Some of them are metastable. So some of them, if we calculate the equilibrium phase diagram, you won't see them. But there is a thermodynamic description. So if you're interested in the formation of delta aluminum copper, you can use it. And it becomes interesting because, it's not in here. Oh, they didn't even put theta in here. Well, in the full aluminum database, there are metastable theta prime and theta double prime phases. So if you've taken a course in thermodynamics or know anything about the aluminum copper system, the aluminum copper system is precipitation strengthened by a theta prime precipitate phase. That theta prime is metastable. The equilibrium phase is this Al2Cu C16 theta phase. But because the theta prime phase and the theta double prime phase are industrially relevant, they're relevant to people that would use this software, they have thermodynamic descriptions for it. And they're pretty reasonable because we have enough experimental data and computational data to be able to describe those systems. For now, I'm going to uncheck all phases and just put together some of the phases to make things easier. I'm going to put the BCC A2 phase, FCC phase, the HCP phase, and the liquid phase. And then if you didn't see it, I did put the AL2CU C16 phase in there as well, because that's theta phase. And so the first thing that I asked it to do, if you remember when I went here, is I did a single point calculation. So the next limb on our tree after system definer, you can look up components too. I've never done anything like that. If you start doing that, you might be beyond me. Same thing with you if you start using ionic species. So that's the way you define a system. Pick your database, define your elements, come over here. If you care which phases you want or you need, you can come over here and you can select specific phases. Default is select all of them that might be stable in the system, all of them with a complete free energy description in this system. If you just want to calculate phase diagram, don't take any of them out. If you want to calculate a metastable phase diagram, for instance, you're interested in what's the equilibrium or metastable equilibrium between FCC copper and theta prime, you would go deselect the equilibrium theta phase, the C16 phase, and just have the theta prime phase. And then you can go calculate a metastable phase diagram. But for now, the easiest calculation is a single equilibrium. And under the equilibrium calculator, you can see that you can basically switch between all of these in here too. There's one equilibrium calculator, and the only difference between single point, one axis, and phase diagram is which button is default in the calculation type. So say we want to know at 800 Kelvin, let's go 900 Kelvin. What is the equilibrium of our aluminum 4% copper? Notice again, we can change our composition unit. We can change our copper concentration unit. If you put something in for the copper content over in the system definer, like I did, it will translate over into this. So now we've defined all of these things. We have a temperature of 900 Kelvin. We have a pressure of 10 to the 5 pascals, which is 1 bar, 1 atmospheric pressure. 1 mole, so we're looking on a per mole basis. Once we define our system, we can say perform tree. It will perform everything along this branch of our tree. And you can watch the event logger calling the database, and it will perform the calculation, and eventually I'm going to change my adapter. This adapter is not so. Now, so for a single equilibrium, it will output something like this in the form of a table. The first set of things are basically defining our system, 1 mole of atoms. We've got a mass of that. which is going to be the weighted average of aluminum and copper. Temperature of 900. This is the total Gibbs free energy, and because we defined 1 mole, this is the molar Gibbs free energy of the system as well. It'll give you the enthalpy. It'll also do the volume. Molar volume of pure aluminum is 10 to the minus 5. And so with a small amount of copper, it doesn't change at all. And then down here, it will give us the stable phases. So at 900 Kelvin, it says we have 2 stable phases. We have a liquid phase and we have an FCC phase. There is 0.23442 moles of liquid, and it gives you the composition of that liquid in both mole fraction and in mass fraction. It'll also give you the volume fraction. A lot of these databases now have this composition and temperature dependent descriptions of the molar volume of each phase, so it can convert from mole fraction to volume fraction. If you wanted to perform a calculation to compare to an experimental measurement of volume fraction of a beta phase in your alpha phase matrix in some experiment you perform, you can go calculate that, compare it to what you observe experimentally. I will warn you, they're not perfect. Maybe for the binary aluminum copper system, they've got a pretty good description. I don't know, but they're never perfect. And a lot of the descriptions are a rule of mixtures, or when it comes to lattice parameters, called Vegard's law, which just basically means rule of mixtures. The lattice parameter of an alloy is equal to the mole fraction of component A times the molar volume of component A plus the mole fraction of component B times the lattice parameter component B. That's Vegard's law. So basically, it's a linear interpolation. Not all of them are that simple. So you do get some excess volume of mixing. I don't know. I don't typically look at the volumes. I've started to look at them when I'm interested in trying to figure out lattice misfit between a precipitate and a matrix. So I've done a lot of work on nickel-based superalloys. Lately, I've been looking at refractory body center cubic B2 superalloys. And I'm not sure how well the molar volume is defined in refractory alloy systems, particularly with a B2 system that is very poorly understood in the refractory alloys. But I can use that to get an idea of what's my lattice misfit going to be between my BCC matrix and my B2 precipitate. And so that's telling me, hey, this is where I want to look experimentally. And so my initial set of calculations gives us 15% ruthenium and X% vanadium and balanced niobium. And this should have a equilibrium of 20% B2 and BCC, and the lattice misfit's going to be X. And so I went and made that. And sure enough, lattice misfit was, reasonably close to X, and it was very high. So it wasn't a nice coherent precipitate. But anyway, those are some of the other things that you can try using. So this is a simple equilibrium calculation. Useful only if you want to know what equilibrium is. One of the things that I do a lot of now is calculating one axis. So say we keep this same system, we stay at 900 Kelvin, and we're going to plot, or we're going to perform a calculation as a function of temperature. And I'm going to start at a minimum of 300 degrees, or room temperature. I'm going to go up to 1500 degrees, which is well above where most of this system will melt, with a step division of 10. Now, if I perform this calculation like this, it's a linear number of steps. under normal step method, it will calculate the equilibrium at each one of those steps. And in some cases that might be useful. The first thing I want to do though is calculate separately. So what this, it's the command is SEP, S-E-P in the console mode, so I call it SEP. But this step method will, instead of calculating the equilibrium at each point, it will calculate the properties of each phase separately for that set of conditions. And what we're going to end up with is, well, can't show it in a table very well. Let's make a plot. Let's say, have I done this in, yeah, let's say the Gibbs energy per mole all the phases in joules. Let's see what I get. Ah. So now this plot is giving us the free energy of all of the phases as a function of temperature for an alloy with aluminum 4 weight % copper. Why might that be important? The lowest Gibbs free energy is stable. So we can calculate delta G. So for instance, one of the things that I've been doing a lot is calculating martensite start temperatures in steels. And the martensite start transformation occurs when the free energy difference between the body center cubic phase and the face center cubic phase, or I should say the face center cubic phase, which is austenite at FCC at high temperatures, and the body center cubic phase, which is the low temperature phase. Martensite transformation occurs when the delta G between austenite and ferrite reaches a certain particular level. And that's basically the activation barrier required for the transformation to proceed. So if I can calculate what that delta G is, and there are other ways to do that, and in fact, ThermoCalc has a module to calculate martensite start temperature. But you can calculate that delta G, you can calculate the martensite start temperature. One of the things that we do in the phase transformations class is we have a liquid of a certain composition. We're going to undercool it. Notice here that the black curve is liquid, the green curve is FCC. Right here it crosses somewhere just above 900, about 907. I bet you if you looked up the phase diagram at 4 weight % copper, that would be right in the middle of the FCC plus liquid region. But above 907, liquid is the stable phase. Below 907, FCC is the stable phase. And actually, when we look at this as a function of composition, we'll end up with 2 equilibrium phases in a certain temperature range. But this tells us the T0. Does anybody know what a T0 curve is? It's the point at which the free energy of 2 phases is equal. This becomes important if you want to form a solid solution, or if you want to quench from a liquid and avoid precipitation of a second phase. Or you want to form an amorphous phase if you want to form a glass. The liquid has a free energy. The glassy phase has a free energy. And the only time that you can go from liquid directly to the amorphous phase or the FCC phase without composition separation is when you're below this T0. Because if you're above T0, at least for this specific composition, the liquid is lower free energy. So there's no driving force for the liquid to go directly into the BCC phase, or FCC phase in this case. If you go below, now you could reduce the free energy if the liquid goes directly into the FCC phase without even nucleating and growing FCC of a different composition or precipitating a second phase. You can go straight from liquid of composition X or 4 weight % copper to FCC of 4 weight % copper. There are lots of other useful things in here, but I'm going to let you come up with those on your own. The most common thing that we will do is, oh, let's just keep using the same thing. Calculate a phase diagram. So I'm going to continue to use the aluminum demo database, but now I'm going to come back here, and when I deleted or when I unchecked all these phases, I did it because if I didn't, it would have given me the free energy curves as a function of temperature for every phase that was checked, and it would be crazy. So I just unchecked everything and checked some of the phases of importance. You can see that there is a description for BCC and HCP, even though we're not going to see it. So to calculate a phase diagram, I'm going to come back here to System Definer, and I'm going to now check all of the phases. Some of them aren't relevant for the aluminum copper phase diagram, but I'm just going to check them all. And now if I go over here, I can calculate a phase diagram. And you can do it as any function. We're going to go a typical phase diagram using mass % copper from 0 to 100. A typical step division is 1%. And again, we'll go from 300 to, I'm going to do 2000 now because I'm not entirely sure if copper melts below 1500 K, but I'm pretty sure it does below 2000 K. So axis 1 is mass % copper from 0 to 100% with a step of 1. Temperature is our second axis, 300 to 2000, and a step of 10. Notice you can also change the temperature. It used to be that if you change the temperature up here in under conditions to say Celsius, it still did the calculation in Kelvin, and it just didn't tell you because it was a glitch in the software. So everything I do now, I do the calculation in Kelvin because that way I know what it's calculating. And then when I go plot things, I will change the axes to Fahrenheit or Celsius or keep it in Kelvin if I want. I believe nowadays they fixed that. So if you want to perform your calculations in Celsius or in Fahrenheit, you can do that. You'll find out ThermoCalc's got a lot of quirks. Even though it's been around since 1990 or earlier, it's still got a lot of quirks. They're still working things out, but every time they send out a new version, it has new quirks. So you'll find that there are lots of quirks. So I've set up my conditions, and now I'm going to perform the tree. And if I go over here, I look at it automatically changed our axes that we want. Under plot renderer 2, now the x-axis will be composition, y-axis will be temperature in Kelvin. And when it finishes the calculation, this initial plot of free energy as a function of temperature will be replaced by the aluminum copper phase type. That calculation will take a couple of minutes. Does anybody have any questions right now while it's calculating? If not, I will go over here to the console mode while we're performing the calculation. And I'll show you how to do the same kind of thing in console mode. Because every command you have in graphical mode is basically calling a command in console mode. And if you're a programmer, console mode may be a more comfortable form mode for you. It's not more comfortable. It's only more comfortable for me because that's what I learned it on. There is some more functionality in certain respects in the console mode. There are some things you can do in console mode you can't do in the graphical mode yet. However, one of the nicest modules that we have, actually two of them, that we have in the newer versions of ThermoCalc are the TC Prisma, or the Precipitation module, that allows you to calculate solid state phase transformations. So say we want to look at the precipitation of the theta prime phase in the aluminum copper system. We can actually, using a kinetics database, we can actually go model that. And we can predict how long we need to age our material to reach a volume fraction and number density and size distribution of precipitates of some desired characteristics. The other nice thing that's in the graphical mode is these property models. And with these, you can actually calculate TTT diagrams or CCT diagrams, time temperature transformation, or continuous cooling transformation diagrams. I believe the CCT only works for steels. It's still pretty cool if you're working for steels, with steels. I've done a TTT diagram, I think, for things not steels, but I can't remember how well that worked. But these are all these different property models. It'll calculate driving forces. There's a crack susceptibility coefficient if you're doing something like additive manufacturing, where you're doing an alloy design to find a casting alloy. Something new is finding a spinodal. Here's the T0 temperature. It'll also calculate yield strength based on solid solution strengthening plus precipitation strengthening plus Hull Petch grain boundary strengthening and some different parameters that it has built in. I've found that the solid solution strengthening, at least what I've looked at, doesn't work very well. So I recommend that if you want to calculate strength of your material, you perform your thermodynamic and microstructural evolution calculations in here, get your precipitate size distribution for solid solution elements, and then take that information and put it in a strength model using the same basic models that are in here that you would find in, say, DICTRA, mechanical metallurgy book, some other strength models, because I don't think they've got there yet using these. I haven't used it in the 2023B version yet, but the last time I tried, I got a yield strength of like 10 megapascals for something, which was a little lower than I would have expected it to be, or a lot lower. So come on. Oh, hey, I've got another window. Oh, that doesn't help because the calculations are over here. Here we go. All right, so our aluminum copper phase diagram is complete. So these lines here, this is basically the legend, and these lines are telling us which phases are in equilibrium across these lines. So this gray line is liquid plus FCC. So this region in here, this is the liquid plus FCC region. I don't normally use, at least when I'm calculating a phase diagram, the standard legend. So if I go under plot renderer, gonna flexible mode, can I just delete my legend option off? That should help. No, you don't need to start the entire calculation over again. All right, so while it's recalculating the thing it calculated, I'll go back over here, console mode. Actually, what I'm going to do is I'm going to use the other window I have open. For console mode, so anytime you want to know what list of commands you have, you can just type question mark, and it'll give you what the list of commands is. A very useful command that I don't use very often is set log file. And if you set the log file, now it will keep track of all of the commands that you input. And then later on, you can run that as a macro file. So you don't have to redo it. I almost never use that. You cannot imagine how many times I put the same commands in to the same exact calculation. But if we want to do something, we want to use the go-to module command, and I know that I can abbreviate it go. And it'll say what module. We can do binary diagram easy. We can do ternary diagram. We can go to the database retrieval. DICTRA, that's the diffusion. Well, actually, that's the diffusion optimization program. So let's do binary diagram easy. So we'll say ask you, hey, what do you want your database to be? Anytime you want to know your list of options, you can just press question mark. Let's use AL demo, which is the same database that we're using in our other one. So we just go AL demo. First element, aluminum. Second element, copper. It'll ask you if you want to plot a phase diagram, phase fraction. which I believe is phase fraction is a function of temperature for a specific composition. We'll calculate just a phase diagram for that. Or you can plot the free energy curves. Let's just plot the phase diagram. Now it will go through the same calculation that our other version is doing. There it is. So here's our phase diagram. I turned the legend off, so we don't have to worry about that. I'm also going to turn the tie lines to 0. Please don't read. Okay, that's good. There. That gets rid of those green. Those green lines were actually tie lines. And for most of what we're interested in, we may only want the aluminum rich side. So I'm going to plot this phase diagram instead to 55%. So up here under axis, we'll switch off automatic scale. Go from 0 to 5. I'm going to turn it to Kelvin. From Kelvin to Celsius. I'm going to change this and go from 100 C to steps of it only needed 700. So 700. There's our aluminum copper phase diagram on the aluminum rich side. So now we can go over and hover over it. If you right click on the diagram, you'll be able to add a label. You could copy the entire diagram, so you could copy it as an image and you can paste it somewhere. You can save it as some type of image file. You could print it, which I've never used. Properties will bring you to all of the options for fonts and labels. So if you wanted to label this, instead of mass percent copper, 8% Cu. So now we've got something a little, change the temperature. You can change the font size. I played around with mine, so the font is pretty good. When I have looking at my normal size monitor, it's a little bit too large when I'm looking at my laptop screen. So the other thing you can do is you can add a label. And when you're looking at a phase diagram, when you select add label, it'll come in, and most of the time it will give you a suggestion. And that suggestion in a binary phase diagram or in a ternary phase diagram is the stable phases. So up here, when I clicked add label up here, I clicked in the single phase liquid region. So it gives me the option of liquid. If you want, you can have it show detail, and it actually will show you the equilibrium. So it'll print out that same data that we looked at for that first point calculation. So in ours, we have 100% liquid. Well, so now we said add label. I'll add the label. There, look at that, right there. All right, so somewhere over here, So here's the liquid plus FCC. Oh, it's a little low. I was trying to go to exactly 900 Kelvin and 3 or 4% copper. But you can see this is pretty close to the same point calculation we have. That gets really nice if you are looking for a composition that has a specific fraction of the different phases. Remember, however, that this is an equilibrium calculation. Oh, that's too big, so I'll go here. I'll modify it. Turn the font down a little bit so it fits in there. And so if you're making a publication or a phase diagram for a publication, you can go in and label whichever regions you want. The default is to give it all of these different top colors. While I've published phase diagrams with all those different wacky colors. Now I tend to go down here under color option, and that's legacy. Let's go printer friendly. Click OK. That's basically black and white. Whoops, there goes mine. I don't know where that went. But printer friendly is basically black and white, and the critical temperatures, like this is the eutectic temperature, that's going to be in red. If you wanted, you could save it as a black and white diagram. This is nice. This is what I've been typically doing. There's all sorts of things. Do however you want. But that's how you calculate a simple binary phase diagram. You go back over here. Hey, look at that. We can get the same exact thing from our bin diagram. So if you're just looking at for a simple binary phase diagram, you can use bin or binary. I think you actually have you have the same option. So this button right here is bin. That's the binary phase diagram. If we click it, it'll ask for element 1, element 2. What type of thing do you want to do? Phase diagram, phase fraction as a function of temperature for a specific composition, or free energy curves. So let's see. That's the simple thing. Does anybody know what a Scheil solidification simulation is? Scheil is another very useful calculation that I use all of the time. What a Scheil solidification simulation is it tells you what to expect in an as solidified microstructure. So if you take our aluminum 4% copper alloy and you cast it, it's only got 4% copper in it, so you might expect it to have all FCC. In reality, because we have non-equilibrium solidification, we get what's called coring in the FCC phase as it solidifies. So the first bit of FCC that solidifies, we go back to our binary phase diagram. Say we have an alloy with 10% copper. If we're up here at a temperature above 630, it's all liquid, right? If we cool it down to the point at which it touches the liquidus, let's say 10% right there, 633 is the liquidus. That's the temperature at which the first bit of solid forms or becomes in equilibrium with the liquid. And the composition of that solid phase that forms is given by the solidus curve over here, which is roughly 1% copper. So the first bit of liquid to solidify is 1% copper. But because we're cooling at a finite rate, when we cool it down to another little bit of a temperature, let's say we cool it down to 600. At 600 degrees of our alloy, the liquidus temperature, or the solid composition that's in equilibrium with the liquid, is 2.5% copper. That's the equilibrium, right? But because we've solidified at a finite rate, we already solidified some of the solid with a composition of 1% copper. And we don't have time to redistribute all that solute to make everything 2.5% copper. So the first bit of FCC to solidify will have 1% copper. Then as it goes down a little bit further, the next bit of liquid will have a little bit more copper in it, and you'll get a composition gradient in your solid. And what a Scheil solidification simulation does is it uses the solidus and liquidus curves of the equilibrium phase diagram to tell you what that composition profile is going to look like. And as you cool down, if you solidify with 1% liquid, you cool down a little bit more. The liquid composition for 10% is actually, for 600 degrees C, is actually way out here at 16%. So once you cool your alloy down to 600, you've got your liquid phase that's going to have about 16 weight% copper in it. And your solidification is actually going to slide, your liquid composition is going to slide down this liquidus curve the further you go in solidification. And eventually, it's going to reach this eutectic point. And at that eutectic point, the liquid becomes completely unstable, and the last little bit of liquid to solidify will solidify as eutectic. And so that's a feature of the Scheil solidification. It is, everything is going to slide down until it reaches the point at which liquid is no longer stable in the entire equilibrium phase diagram. And so that last little bit will form as liquid. Is that realistic? Well, it depends on exactly what you need. The curve, the composition curve, is going to be quite good. When you get out to the last little bit to solidify, you start to get, a lot of solute enrichment in the liquid. Eventually, you'll go below a T0, and you'll be able to solidify. So you may not actually see all of the eutectic, or you may not see eutectic depending on what your starting composition is. But in a lot of alloys, even alloys in this aluminum copper system, and actually this 4% copper alloy that we started with, you might actually see eutectic solidification in the final microstructure. And I know that for some of these that are slightly above this maximum solubility, so a 6% copper alloy, you're going to see in an as solidified microstructure eutectic FCC plus theta phase. But what the Scheil solidification does is it uses that equilibrium phase diagram, and we'll use the aluminum copper system as an example. We'll go aluminum and copper. We're going to ignore species. I'm going to keep all of the phases in here for now. Under Scheil, it'll ask you for a starting temperature, default of 2500. I'm going to use 1500. Calculate it from the liquidus. Temperature step during Scheil, if you want to do by default, it's going to do a new calculation every 1 degree. So it'll find the liquidus, calculate that equilibrium, and then cool down a little bit more, calculate the new equilibrium compositions, calculate how much solid forms between the liquidus and 1 degree below the liquidus, and so forth. So let's do that calculation. I've actually never done one here. And then I'll probably quit for the day because I don't want you guys to listen the whole time. And there are a number of people that want to watch this on video, so I don't want to make it too long. If any of you have gone to phase-trans.utk.edu, you will find that there are similar tutorial sessions that I did, I don't know, 3 years ago or so, 2 years ago or so, and some of them could be 2.5 hours long. And if you haven't noticed, I do like to talk. If you had me in class, you know I really like to talk. If you've done research with me, you really, really know I like to talk, as I am right now. But I'm doing my best to not go too far off on tangents to keep it a little bit more bearable for people watching the video. The tangents I do go off on, I'm trying to keep to something relevant to ThermoCalc experiences that I've had and so forth. So what we get when we do a Scheil solidification calculation is the first thing that pops up is it will give you the mole fraction of solid on the x-axis and temperature on the y-axis. And what this is this tells you the temperature at which 20% solid will have formed. So our liquidus here is about 650 by 647 will have formed 20% of our total solid. By 640, it'll be about 50%. And the colors associated with this tell you what phases are there. So initially at x equals 0 here, there is a black line where only liquid is stable. But the first phase to form is FCC, so this red line says is liquid plus FCC, and then this green point right here is the point at which I showed you the alloy has reached the eutectic point. So the composition of liquid has reached the eutectic point, and at that point, single composition or single temperature in a binary alloy of 548. That's the eutectic temperature for aluminum copper. We have the last bit, it looks like about 8% of the alloy will actually solidify as eutectic FCC plus Al2Cu C16, which is the theta phase. Something else that might be useful is when we go down to this plot, I might plot the volume fraction of a solid phase of different phases. Oh, that's volume fraction of all phases. I want. just easier in console mode. Maybe. I don't see anything, so I have to put them both in there. But if I put them both in here, so right here I plotted the volume fraction of FCC as a function of mole fraction solidified. Here I've done the aluminum copper. So now I can look at the okay. Won't even let me. Ooh. One last quick calculation. So go to the console, go SCH for Scheil. We'll start. ST stands for start. If you do this in the console mode, if you do a Scheil calculation, go Scheil or go SCH. ST stands for start. It'll ask for what database. We will use AL demo. Then it'll ask what's the major alloy, major element, aluminum, composition and weight percent. For now, we'll use yes. If you say no, you can input in mole percent. Depending on what you're doing, it's more useful. If you're dealing with commercial alloys or derivations of commercial alloys, you're going to do weight percent. If you're dealing with high-entropy alloys or something, you're going to use atomic percent. So our first alloying element is copper. It'll ask how much, 4. Second alloying element, we're just going to do a binary alloy. We'll start at 1500 for a temperature. There's the database. This one will ask us if we want to reject any phases. I'm not going to reject or restore any phases. Yes, that's the right phases. And so now it will perform the same calculation it will just do. What we just did, should a miscibility, any phase have a miscibility gap? I think it finds it regardless of what you say. That's left over from before we had global minimization, which is a methodology for finding global minimum versus fast diffusing components. If we had something like carbon, we could do a fast diffusing component like carbon and allow carbon to actually diffuse in the solid. But most of the time, no fast diffusing components. Calculate, calculate, calculate. All right, let's look at that. It's the same thing we got in the graphical mode. Now I'm going to use set diagram axis to change the y-axis from temperature to the mole fraction of each phase. So set diagram axis S-D-A y ns, which stands for the number of moles of solid phase. And in parentheses, I'm going to put a star. That's a wild card, meaning all phases that it found. If I wanted just to see what the volume fraction of FCC was as a function of temperature, I would have put FCC in there, but I'm going to put star in there. And I'm going to set the labels equal to F. That's something we can talk about some other time. But when we calculate that, this actually will tell us, hey, this is how much of each phase we have. This is when it forms. And it's not so interesting in here, but as the punchline for the day, I will show you a Scheil solidification for one of our aluminum cerium alloys. So this is a Scheil simulation for a more complicated aluminum, cerium, magnesium, copper alloy. And it tells us the amount of each phase and when it forms. So first phase to form is aluminum 11 cerium 3, but I'm almost right on the eutectic point in this ternary or in this multi-component alloy. So almost immediately I start forming FCC plus the aluminum, cerium, and metallic until I get out here to about 80%, and then I start forming all of these different other phases in here. And when we go look at the microstructure of this alloy, we can compare. Hey, do have about 9% aluminum 11 cerium. We do have about 5 or 6% T phase. Some of these other phases don't actually form. We might have some S phase, but that'll tell us exactly what we expect to see in our microstructure. We can set diagram axis Y, W, FCC, A1, comma, CU. When we plot that, this is the composition profile. So I mentioned we're going to have what we call coring, where the first bit of solid to solidify is going to have one composition, and it's going to increase, increase, increase. So if we go take our as cast aluminum copper alloy, we take it into the SEM and we do a line profile from the center of a dendrite to the dendrite core, we will get a composition profile. It will match this quite well, very well. So if you want to know how much segregation do you get, what's that composition profile look like? Boom, you can calculate it. And then if you're interested in a homogeneous alloy, this difference in composition will help you determine appropriate homogenization or solutionization heat treatment to eliminate that composition profile, because now we've got multiple dendrites that have 0.5% copper, and then we've got multiple interdendritic regions that have 5 to 5.5% copper. You look at your microstructure, you'll see it has a fairly regular spacing, which is called the lamellar spacing. And based on the lamellar spacing and the delta in composition, you can go find out what the diffusivity of copper is in aluminum, see how long is it going to take for me to solve the diffusion equation for sinusoidal composition, and find out how long you need to heat treat it to get rid of all of this composition segregation. That's it for today. Anybody have any questions with what I've gone over? Did everybody get at least something out of it? Yeah. Yes. Do you want me to increase the font size in the console mode? You can't read it. Okay. Okay. I will see what I can do. I wonder if there's a DMAG like there is on the SCM that I can just zoom in to do. It might be possible if next time you sit over closer to that screen. Sometimes we'll be across the hall in 140, and I think next week we actually are across the hall in 147, so we'll have the big screens. I do apologize. It's not easy to read. One thing I could do is share the Zoom link that I'm recording it on, and that way you can see it on your screen. It becomes more difficult to, jump back and forth if you want to try copying, doing what I'm doing. That becomes more difficult. I'll see, but I don't think I can increase the font in the console mode, but I'll try. I'll see what I can do. Any other questions? Yes. We are within a single instance of ThermoCalc. Like we open ThermoCalc here. The calculations you perform in console mode are completely separate from the calculations you perform in graphical mode. They are basically two completely separate things. I mean, you can do the same calculations, but you can't do a calculation in the console mode and then like move it over to the graphical mode. You're going to have to go over to the graphical mode and do that same calculation again. Anything else? Was it useful? Just a little bit? All right. So we'll plan on doing this. I'll keep going over some of the basics over the next several weeks. Please, if you have questions as we're going along, Tao, I wish you would have said I can't read it. I would have tried to figure something else out, or we would have moved you so you could read it. But if you have questions while we're talking, please feel free. I want this to be more of a conversation than anything. I don't want it to be a 2-hour lecture on ThermoCalc. I want this to be something where you guys are learning some things that you don't know, lecture style, but interact with me. So you say, hey, what if I wanted to do Y instead of what you just showed me? We can do that. And then maybe 4 or 5 weeks from now, when I've shown you all the basics, you guys can come to me with questions that are specific to your own research. And we can try to set up some version of what we're doing. So with that, I'll let you go. I will say, if you did not email me and let me know, you're not on the list. So I have an Outlook calendar invite, and everybody that sent me an email, I put on that calendar invite. And if I have any updates or I'm going to cancel or something like that, I'm going to reply. I'm going to send an email to everybody on that calendar invite. So if you're not on that calendar invite, please send me an email and I will put you on that so that we can all communicate together. Okay? There was something else I was going to say, but I've talked way too much today. So go forth, enjoy Thermo. Oh yeah. If you get to the point where you want the full version of ThermoCalc because it's going to be useful for your research, come talk to me and we'll get that up and running. Okay? For now, I've given you the demo version because I know some of you just want to learn how to use it. If you find that you're going to use it in your research, there's no problem. We just go put it on your on your machine, just like we did this one. It's just, it needs to stay relatively closed. It's not an open license to the entire university. It's for research purposes, and I think we can get some access to additional databases if we wanted to do something educational. I know when I taught the ThermoCalc course, we gave licenses to the full version for the summer so that people could use the full databases. But anyway, if you want the full version because you're going to use it, come find me. And if you know Python and you are planning on learning how to use the TC Python interface, once I am done teaching you ThermoCalc, I want you to do me a favor and teach me the TC Python interface. Have a good afternoon, everybody. Thanks for coming. I will see a lot of you over the next few days. Otherwise, I'll talk to you next Wednesday. And I will post this on phase-trans.utk.edu. And apparently, I'm going to also start putting on a YouTube site so that I can actually track whether or not people are actually using it, which is kind of cool. And then we can start putting other things on them. Anyway, bye, everybody. Thanks for coming. I hope you are getting something out of it. Take care.